Okay, can anyone hear me? Okay, can you guys let me know if you can hear me? Okay, okay, great. Thank you very much for coming here. And I think today's lab is gonna be the last one, and I will double check with Dr. Kim. And also for the homework assignment, um, I think we might have one more, or we just gonna skip that too. So I would definitely talk to Dr. Kim about that. Hopefully we can just like reduce some amount for the homework assignment, and but I need to talk to Dr. Kim first to see if we can just skip the two homeworks. So um, I will keep you guys updated when I got the information from him. And if you have any concerns or questions, just let me know. And I think Dr. Kim is preparing for the finals, and maybe this path analysis is in the final. So I think today's lab is kind of important for you. So if you have any concerns or any things that you cannot understand that well, just let me know, and I will slow down or I will just repeat what I just presented. Okay, so for today's topic is a path analysis, and I think the material in this lab is not that well designed, but I will try my best to explain it. Because in the past, like the material is done by SPSS, and it's done and I think in the textbook it's done by like a very elementary or like naive way to do the path analysis. It's not a very comprehensive path analysis, um, but you will get like the basic idea. So let me introduce the way that introduced in the textbook, and then I will just use another package called Lavaan in R to let you know how to use the package to conduct the path analysis. Okay, so let's get started. Okay, so there are some terms to for you to know today. Um, so let's go through it one by one. The first one is called endogenous variables. So those are the variables that are being explained by the model. You can think of those variables as the dependent variable. Um, for the exogenous variables, those are the variables not being explained by the model, which are the IVs. And then later is the direct effect and indirect effect. So the direct effect is a variable directly affects an endogenous variable without intervening variables. So you can see that later. Um, and then the indirect effect is a variable affects an endogenous variable with the intervening variables like mediators. And for the path coefficients, so those are the change in the dV with one unit change in IV while holding the other IVs constant. So pretty much the path coefficients are similar to the beta coefficients in a multiple regression. And for the last term, it's called disturbance. So for the disturbance, it's the composite effect of any other direct determinants that are not included in the model, plus the measurement error, like the residual in the multiple regression. Okay. Okay. So let's move on. So here we're going to talk a little bit about the components in the path diagram. So as you can see that the first one is the observed variables. For the observed variables, we're using the squares or rectangular, the rectangles to represent the observed variables. For the latent variables, we're going to use the circle or ellipses. But in this case, a path analysis, we're not going to use the latent variables here. All the variables you can see are observed variables. And for the third one, for the hypothesized directional effects of one variable to the another, or the direct effect, we are using a line with a single arrowhead. For the covariance or correlations, we are going to use the curved line with two arrowheads. Okay, so this is the components in the diagram. Oh, actually, for the latent variables, since the disturbance is unobserved, we're going to use the circle. So so we have the observed variables and the latent variables in our path diagram. But you can see here our observed variables themselves are not latent variables, so it's represented by the rectangles. Okay, so here we have a path diagram as an example. So we are going to use this path diagram later for our lab today. Here you can see we have 5 variables here. So the questions here are what are the exogenous variable and what are the endogenous variables here. So I think it's already given. The answer you can find the answer here. So for the Z1 and Z2, those two are the exogenous variable, and Z3, Z4, and Z5 are the endogenous variables. Okay, and the intervening variables, the mediator, you can see here is the Z3 and the Z4. Okay, and disturbance is just here, here, and here. Okay. So we can specify 3 expressions here. So the 3 equations is explained by this. Can explain this path diagram. So the first one is a Z3 is equal to P31 times Z1 plus E3. So you can see it's so this one is representing this relationship. So it's the relationship between Z1 and Z3 here. Okay. So the second one, Z4 equals to P42 times Z2 plus E4. So this is this equation here. Okay, it's a relationship between the Z2 and the Z4. And the next one is Z5. So as you can see here, the Z5 is explained by Z3, Z1, and the Z4. So we have P51 Z1 times P53 Z3 plus P54 times Z4 plus E5. Okay, so here we have the structure equations here, the regression equations. Okay. So Next, we're going to talk a little bit about the path tracing rules. So this, with the path tracing rules, we can calculate the model implied correlation matrix. So we highlight all the possible routes between pairs of variables and multiply compound path within a route, and then we add up all the possible routes. And for the path tracing rules, uh, you have to follow some rules here. So first is no loops. You cannot go through the same variables twice in a single route. And the second one is a no going forward and then backward. So you can go backward first and then forward, but you cannot go forward and then backward. And the next is like a maximum of one double-headed arrow, or like we mean correlation here, per path. Okay, so in this case, you can use the path tracing rules to find out all the possible path in this path diagram. Okay, so usually in the lab, like if we are physically meeting in the lab, we can do this exercise, but it will be a little bit hard to explain that or do the exercise here. So I'm just gonna tell you the answer. You can find all the possible path here. So let's just put this here, and I will find another thing. I will find the path diagram on the side of that one. Let me see if I can do that. Okay, I think I could do this. So I just put this two things side by side so you can take a look. Okay. Uh, okay, so okay, so here you can see, um, so the first one is the correlation between Z1 and Z2. So it's the R12, it's just here. The next one is R13. So R13 is just the P31 here. Okay. So for the path coefficient, the first subscript represents the endogenous variable, and the second subscript, it means the exogenous variable, or the variables like so the first subscript is the variables represents the variables that the arrow pointing to. The second subscript is the where it come from. Okay, so R13 equals to P31, so it's from Z1 to Z3, right? So R14 is from Z1 to Z4. Okay, so from Z1 to Z4, we have a correlation here, so it's a R12, and then we go through from Z1 to so from Z1 to Z2 and from Z2 to Z4. So we have so that's why we time the R12 to the P42. So this is the relationship, the correlation between 1 and 4. Okay. And then for the R15, we have multiple paths here. So the P51 is this one, right? The P51 is the direct effect from Z1 to Z5. The second one is the P31 times P53. So you can see here from Z1 to Z5, we have this path here. So from Z1 to Z3, from Z3 to Z5. So we time these two together. And plus the last one actually is going down here from Z1 to Z2, Z2 to Z4, and Z4 to Z5. So we have R12 times P42 times P54. Okay, so this is relationship between so this is correlation between 1 and 5. And next is a R23. So for R23 is from 2 to 3, right? So from 2 to 3 we have only one path, which is R12 times P31. And next is a R24, R2 to so Z2 to Z4 is just P42. Next is the R25. So from Z2 to Z5, actually we have a lot of path here. Again, first is a P42 times P54. So it's a Z2 to Z4 to Z5. Next is a Z2 to Z1 to Z5. Okay, so that's R12 times P51. And the last path is from Z2 to Z1 to Z3 to Z5. So it's a R12 to times P31 times P53. Okay, so that's this one. And next is the R34. So it's from R3 to R4. We can go back one time. So from Z3 to Z1 to from Z3 to Z1, from Z1 to Z2, and from Z2 to Z4. So it's a P31 times R12 times P42. Next is R35. So we have three paths here. From Z3 to Z5, we can directly go through the P53. Next is going backward, P31 to so we go to the Z1 here, and then we go directly to Z5. So P31 times P51. Next is the Z3 to Z1 to Z2 to Z4 to Z5. So it's like going around, right? Like this way. So the P31 times R12 times P42 times P54. Okay. The last one is the R45. So from 4 to 5, right? So you can directly go through here. So it's a P54. Next is a go backward one time, P42 times R12, and then go directly to Z5, so P51. So it's this. And then the last one, the last possible path is the go from Z4 to Z2 to Z1 to Z3 and Z5. So it's P42 times R12 times P31 times P53. Okay, so here we have all the possible paths found out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 here. Okay, so that's how you calculate it. Okay, so any questions to find out the paths? So all you need to memorize is just the path tracing rules here. So there are some limitation. I mean, there's some things you cannot do. Okay, so based on this slides, you can just count all the paths out. Okay. Okay, so after we did this path tracing rules, next we can use that to calculate and the model implied correlations. So we are going to do that later. We can definitely utilize R to calculate for us. But as a practice, we're just going to do that sort of like kind of like naive ways to do that. So you can see that in the code later. Okay, so after we calculate the model implied correlation matrix, we can compare that correlation matrix with the observed correlation matrix. So if our observed correlation matrix is very close to the model implied correlation matrix, we have a good model fit. So it just means that overall the path model we specified based on either the theory or other things, it has a good fit. It explains the data very well. Uh, but if there's a large difference, we have very poor model fit, and we should revise the model in which we'll explain that later. Okay. So we know there's a poor model fit if the difference, the individual differences in the correlation is greater than 0.05. Okay, so this is like a general rule here. I didn't check the source of this rule, but it's just mentioned in a textbook, so you can definitely check out that later. Um, okay, so here are the steps to do the path analysis in the textbook way. So first, you calculate the you create the observed correlation matrix. So this is easy, right? It's just the correlation between each variables you're interested in, and then you specify the path model based on the theory, and then you can run the first set of regressions. So here you can check whether the paths are significant or not, and you can include or exclude some of the paths based on your result. Next, you can create the path decompositions based on the betas from the step 3, and use that path decompositions to create the reproduced or also called model implied correlation matrix to compare to the observed correlation matrix. If there are too many values that are different from they are different, which is greater than 0.05, you need to run the regression of the missing paths. So if necessary, so run the regression of the missing paths and the old paths. So you basically run all the paths to find out significant paths to include in your path model, and remove some of the remove all the insignificant path. In this way, uh, you just run the regression by using only the significant paths. So and then use the beta coefficient estimates to calculate and create the path decompositions and create the model implied correlation matrix, the new revised uh, uh, reproduced correlation matrix to compare to the observed correlation matrix to check the model fit. Okay, so this is how you do that. Okay, so we are going to go through that step by step by using this example. So we are interested in developing a causal model for explaining infant mortality. So the causal effect of the following variables will be evaluated. The first variable is the number of doctors per 10,000 people. So the variable name is called docs. The next is the gross domestic product, GDP. And the next is the death rate per 1,000 people. So the variable name is death rate. The next is birth rate per 1,000 people. So it's birth rate. And then the last one is the infant mortality per 1,000 live births. So the variable name is infant mortality rate. Okay. For the first two variables, we're going to take the log, so using the log transformation. So the variable name will become the ln docs and the ln GDP. Okay. And this is the data set we're going to use. Okay, so we have two research questions. So first is our model consistent with our observed correlation among these variables? This is the first one. Second, if our model is consistent, what are the estimated direct, indirect, and the total causal effects among the variables? This is a second question, right? So let's do the first step. So first step is just to create the observed correlation matrix. So that's when we going start to go through our code here. Okay. So I think I upload the title wrong. It's like now it's lab 9. So change that to lab 9. Okay. So there are some packages we're going to use. Be sure to install the packages. I think I didn't put the package Lavang for installed, so you can install the Lavang and this HMISC if you didn't install it. So install all the packages and load them. Okay. Then we can read the data. Okay, I already did that. And then this is optional, but you can just select all the data, all the variables you want. So you can see here we have 5 variables here: ln docs, ln GDP. So those are the log of those 2 variables, and death rate, birth rate, and the infant mortality rate. Okay, so we run this. So we select we subset the data set here. Next, we are going to get the observed correlation matrix here. So it's just called the R-core by using the R-core function in the HMISC. Okay, and we print out the correlation matrix and also our a significance test for the correlations. Okay, so as you can see here is the correlation matrix as I put it here. Okay, this is the first step. We're going to compare our model implied correlation matrix later on with this observed correlation matrix. So keep that in mind. Okay, we're just going to use this later. Next, we are going to specify our model. So in this case, we're going to put our variables here. So this path model is exactly the model you see before. So Z1, Z2, Z3, Z4, and Z5 are this is ln docs, Z2 is ln GDP, Z3 is death rate, Z4 is birth rate, and Z5 is infant mortality rate. Okay. So we create this path model based on the theory. The third step is to run 3 separate regressions to get our path coefficients. Okay, so we have 3 equations here. It is identical to the structure equations you see before. Okay, the regression equations. So I think you already know how to do that. So you can see in the code EQ1, equation 1, equation 2, and equation 3 are corresponding equations to the slides. So you can just run these 3 and then get the summary for the 3 LM objects. So here are the results. Then let's see the result. Okay, so this is the first result. You can see that the ln docs, this path coefficient is significant, and that's why we're going to use this path, right? We're going to include this path. So the path coefficient is here, and in order to calculate for the correlations, we need to get the standardized beta estimates, the standardized path coefficient estimate. Okay, so that's why we are going to use the code ln beta, and then this the coefficient here. So this is how you can get the standardized beta estimate. Okay, so this is very, very important. So keep that in mind. And here, this one is how you can get this number here. Okay, so this is P31. So you can see P31 is here. Okay, we got that. Next is the second model. Okay, the second equation. You can see here the ln GDP is significant as well. So we're going to use the standardized estimate result, and we do that. Actually, I'm also going to run the total everything here. So for the second equation, you can just do the same thing. So you can see here. So this P42 is our path coefficient for the here. Okay, for P42. So far, we already get the P31 and the P42. Okay, and the last equation, we will get the P53, P51, and P54. Okay, so let's look at the last one. So you can see here all the path coefficients are significant, and we are going to use them all, right? So here you can get the standardized estimates, and here these three are the P51, P53, and P54. Okay, already got those. Then since we already get all the path coefficients, and also all the path coefficients are significant, we're all included that, right? So then we are going to use the path decompositions. We use based on our path tracing rules. Let me find that out here. Okay, so as you can see here, here are exactly the thing I write down here. So you can get all the model implied correlations based on the path decompositions. So okay, so this is how you specify that. So the R12, right, is the correlation between Z1 and Z2, the exogenous variables. So this is from the original observed correlation matrix. Okay, so the first correlation, I think it's the second row and the first column. So that's the correlation between the Z1 and Z2. So you can get from there. Later, you can just use the path decomposition to get everything here. So I just run it here. Okay, so with this you can just get all the correlations already, and okay, so these two screenshot from the textbook is basically the same thing we're talking about. So we already did this. Okay, so this is just a calculation, and then we are going to put those correlations into a matrix. Okay, here, and then we can compare the observed correlation matrix with the reproduced correlation matrix we did. Okay, it is optional to put that into a matrix. If you well, in the code, I didn't write it down. I didn't put that into a matrix. I just write it in this way. So and you can see here, this is just to call out all the differences here. So okay, so you can check if the difference, each individual difference between the observed correlation and the model implied correlation is greater than 0.05. Okay, So if there are a lot of the differences which is larger than 0.05, it indicates that we have a poor model fit. And based on this table, which is the same thing, right? So here, 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 here. So 1, 2, 3, 4, 5, 6. So we have 6 correlations that has difference greater than 0.05. So maybe we are missing a lot of paths here, okay? Or we based on our theory, maybe our data doesn't fit, okay? So that's something we need to do a little bit. Okay, so from here, we are going to specify all the paths. As you can see here, we specify all the paths. So for the death rate, birth rate, and infant mortality rate, you can see we are predicting those by all of the variables here. Okay, so those 3 equations are the regression equations we're going to run now. Okay, let's just run these 3 and get the model summary. Okay, so we run these 3 to check if there's any significant path here. So for the first equation, you can see here the ln dox is the significant, right? So that's the only path coefficient is significant predicting the death rate. So for the ln GDP and ln and the birth rate, those 2 are not significant path. So we are not going to include those 2, but only include the dox for predicting the death rate. Okay. Next, for the birth rate, you can see here the death rate is not significant, so we're not going to include that. So only the ln dox and the newly added ln GDP is going to predict the birth rate. Okay. Let me see. Yeah. Next, for the infant mortality rate, we have 3 predictors predicting the infant mortality rate significantly, but for the dox variable, it's not significant, so we are not going to use that. Okay, so this in this step 7, this is the final revised model, path model we're going to run. So we have 3 structure equations here to structure our path model. So we have dox and the GDP predicting birth rate, and the death rate, GDP, and the birth rate predicting infant mortality rate, and only the dox predicting the death rate. And to visualize that, actually the model is at the end. So you can see this is the model here. However, in this case, we need to still do the same thing like we did in step 4. So after we run the model, we need to get all the path coefficients, and then we do the path decompositions to get the correlations, the model implied correlations, and then we need to compare that to the initial model, to the initial correlation matrix. So those steps are not included, actually, are not included in the code, but those calculations are actually already indicated in the slides. So those are all the calculations you can use. And then we are going to do the same thing here. We compare the observed correlation matrix with the revised reproduce a correlation matrix. Okay, model implied correlations. So you can see here, this is the original one. This is the one with the initial model based on the theory, and this is the revised one. Okay, that's the last part. And for the textbook, it doesn't use the lavaan package, but I would like to just add a little bit more, like to let you know how to use the lavaan to do the path analysis, like a very simple one using our example. So basically, for the lavaan package, first you need to specify the model, and then you need to use either the raw data or the correlation matrix, or the covariance matrix to be your data. Okay, so I use the covariance matrix as our data. So it will be much easier for me to do that. So let's see how to use lavaan to do the path analysis. So first, you need to specify an object as our model. As you can see here, I indicate those variables with a little bit extra name like Z1, Z2, Z3, Z4, Z5. In this case, you can just find them out. So which is which variable you're indicating. So that's just convenience. Okay. So you can see here the three equations are exactly same based on our theory. Okay. Which is here. Okay. I think it's in slide 17. So it's the same here. And then we specify the covariance between the first two exogenous variables, Z1 and Z2. And we have all the variances for every single variables in our model. Okay, so here you can see here like this two tilde. So those two are indicating the either the covariance or the variance, depends on. So you put like two variables before and after, and for the covariance is you put different like two different variables to indicate the covariance. If you put the same variable name, it will become the variance. Okay, so this is very easy. So this is how you specify the model, and then this one is the correlation matrix. The only information we need is just half of the correlation matrix, because our correlation matrix is a diagonal matrix, right? It's like we only need half of the information. So actually, I just copy and paste the correlation matrix here. So you can see this is the half correlation matrix. If you go up and then you run this print here, so this is the full one, right? So we only need half of it. So I just copy and paste and delete half of them to put it here. Just if you guys know how to do that like quicker, feel free to share. But I just copy and paste the number here to create this correlation matrix object. Okay. And then for our lavaan package, we need to get the covariance matrix, not the correlation matrix. So we need to use the getCov, this one, to change our correlation matrix to a covariance matrix. And I just use this to change that. So this is the object of our covariance matrix. And then use the SEM code to put our covariance matrix as our sample covariance matrix. This is our data. And then for the model, we are going to use the model object we specified before, and put the sample number of observations here. We have 122 observations, and then we call out the summary for this Lavang object. Okay, so if you can see here, oh, I didn't specify the model. Okay, and okay, so this is our summary for model summary for the Lavang package. Here you can see some of the model fit indices. I think those are more covered in the SEM course, but still you can see like the chi-square test statistics, and also the like AIC, BIC, so many model fit indices here. I think those are. I'm not going to go through that detail very very well. But what I want to let you know is the how to get the how to get the model implied correlation matrix in one code, which is the inspect fit. So what equals to core.all, and this code with this code you can just directly get the correlation, the model implied correlation matrix. Like here we calculate a lot, right? We calculate how, like, using the path decompositions. It's kind of annoying and tedious, but here we just get directly. Actually, there's some differences for everything, the correlation with the Z5, but the difference is not that much, so it's pretty much identical. However, please pay attention to the order of the variables here. You can see here the first one is variable 3, Z3, Z4, Z5, and then Z1, Z2. This is kind of weird. I don't know why it just gives 3, 4, 5, and then 1, 2. Why not? It's just 1, 2, 3, 4, 5. It's kind of weird, but still, like, the order doesn't matter if you just check it, the numbers, and to see if the difference between this correlation matrix and this model implied matrix has like individual differences larger than 0.05, right? Just you can compare this correlation matrix with this matrix here. Okay, so later you can just re-specify your model and then do the same thing to call out this model implied correlation matrix and compare with this correlation matrix here. Okay, in that case, you can just quickly check your model fit. Okay, this is how I would recommend you to do. But still, you need to understand everything before, like using this path tracing rules to find out all the paths, and then use the path decompositions to calculate the model implied correlations, and compare that with the observed correlations. Okay, so that's it for today. I'll definitely let you guys know how to like for the later like homework, if we have homework, and I will definitely ask Dr. Kim about the assignment and the final. Okay, so let me know if you have any concerns or questions, and I hope to see you guys next semester. Thank you very much. Okay, so I will end this live stream now. Okay, thank you. Bye.